Good morning, my dear students. Welcome to the series lecture on EC 402 Nanoelectronics of Kerala Technological University. Today, we are going to discuss about the resonant tunneling diode. In the last class, we have discussed about what is meant by resonant tunneling effect and how this effect is used or utilized for the operation of heterojunction devices. Today, we are going to discuss about the structural details and operational characteristics of tunneling diodes or resonant tunneling diodes of heterojunctions. Resonant tunneling diode is a quantum well structured semiconductor device that uses electron tunneling. It has the unique property of negative differential resistance on its current voltage characteristics. The operation of entire quantum well electronic device is based on the resonant tunneling effect, that is RTE, which takes place when the current travels through a structure formed by two thin barriers with a quantum well between them, which is shown in the energy band diagram. We will see that. Now we will see what is the structure of an RTD or resonant tunneling diode. Let us consider the figure here. For an example, aluminum gallium arsenide resonant tunneling diode is shown here with its arrangement of different layers. The heterojunction is formed by high band gap material aluminum gallium arsenide and lightly doped gallium arsenide material. The lightly doped gallium arsenide layer is grown over a heavily doped N-type gallium arsenide material substrate, which facilitates for ohmic electrical contacts to the device. Aluminum gallium arsenide layer is grown over this layer, between which the quantum wells are formed. We know that when heterojunctions are formed, there is always quantum well formed between the junction. Over the aluminum gallium arsenide, heavily doped N-type gallium arsenide is grown for ohmic contacts to the electrical connection, which is shown in the schematic diagram here. See here, this is the structure. This is the N-type gallium arsenide substrate, which is heavily doped, over which an aluminum gallium arsenide barrier layer is here. Then this is the gallium arsenide, that is the collector, which is lightly doped one, and here over this collector gallium arsenide, again there is a aluminum gallium arsenide barrier which is formed, over which N positive, that is heavily doped gallium arsenide layer is made, over which the metallic contacts is there. Here the collector contacts are taken from the heavily doped gallium arsenide on the collector side, and the emitter contacts are actually taken from the heavily doped gallium arsenide on the emitter side. So this aluminum gallium arsenide is the emitter, which is having sufficient electrons available on its band structure, and gallium arsenide, that is the collector. So here this aluminum gallium arsenide, there is a heterojunction formed. Here also there is a heterojunction formed. So between these heterojunctions, quantum wells are formed. So this is a double barrier structure as shown here. This is a double barrier structure. One barrier is here, the another barrier is here, and between these barriers, quantum wells are formed. And this is the electron from the emitter side that is injected on this or that is penetrated through this barrier to the quantum well. When the energy level is increased or resonation takes place, or resonant condition takes place. Now we have to see the operation of this quantum well and this RTD. So this is the figure A, which shows the conduction band of a double heterojunction with a quantum well between these junctions. So this is the quantum well formed, and this is barrier 1 and barrier 2. This two barrier, this is the emitter barrier, and this is the collector barrier. And here the thickness of this quantum well is about 5 to 10 nanometer. That is to allow only one electron energy level, that is E1 here, electron energy level E1. Now let us consider the case of the energy band structure shown here. Here this is the emitter side and this is the collector side, and this is the quantum well formed. And let us consider the operation of this one. The Fermi level of the N positive gallium arsenide. N positive means heavily doped gallium arsenide is represented within the conduction band. Here the Fermi level of the contacts, metallic contacts, which is represented within the conduction band here, that is here, the conduction band here. Since it can be considered a degenerated semiconductor, when there is no forward voltage bias applied, that is V is equal to 0, when there is no biasing voltage applied, most of the electrons and holes are stationary, forming an accumulation layer in the emitter and collector region respectively. So when there is no voltage applied, so what happens at the emitter side and collector side, this electrons and holes are actually accumulated. So now when a forward voltage is applied, an electric field is created that causes electron to move from the emitter to the collector by tunneling through the scattering state within the quantum well. See here, when the biasing voltage is applied, so here this is the condition when there is no bias voltage applied. When the bias voltage is applied, so here the electric field which actually makes the condition of electrons which penetrates through the barrier, and here the energy, the electrons which are actually already accumulated here will be passing through this, or that will be penetrating through this barrier and reaches this quantum well. And quantum well, okay. So that actually that penetration is taken by the tunneling effect. So what is the tunneling? That is the energy of the applied electric field is at resonance with the energy of the quantum well. That is the energy of the applied electric field is at resonance with the energy of the quantum well. Then maximum penetration of electrons from the emitter to collector is taken place through the quantum well. And now the electrons in the quantum well is now in the quasi-bound energy states. So this quasi-bound energy states are the energy states that allow electrons to tunnel through, creating a current. As more and more electrons in the emitter have the same energy as the quasi-bound state, more electrons are able to tunnel through the well, resulting in an increase in the current as the applied voltage is increased. It is shown in the VI characteristics, that is here. You can see when the electric field is increased, that is the biasing voltage is increased, more and more electrons are penetrating through this one. So penetrating through this barrier and reaches at the collector side, so that what happens here, this current IV characteristic of the device is taken. This current is gradually increased from 1 to 2 and reaches to a maximum value at a particular voltage of the bias. That voltage is usually called a VP. That is the voltage at which the current is at its peak current, at which the voltage is VP. Now see what happens. When the electric field increases, that is biasing voltage is increased further to the point where the energy level of the electrons in the emitter coincides with the energy level of the quasi-bound state of the well. That is, the applied electric field is making in resonating or resonating with the energy level of the quasi-bound state of the well. And the current reaches a maximum value, that is the point 2 in the IV characteristic. At the bias voltage Vp that we have seen, see here the current reaches the maximum value to 1 to 2, and that voltage at which this current peak is taken place is Pp, which is not shown here in this IV characteristic. Now, as applied voltage continues to increase, more and more electrons are gaining too much energy to tunnel through the well, and the current is decreased to a minimum value IV, the valley current. So here we have seen when the applied voltage is further increased, more and more electrons are tunneling through this particular quantum well, and what happens, but at the same time the current through the device is getting decreased and reaches to a minimum value IV, that is what is called the valley current at a particular voltage, what is called the valley voltage. So this valley current will be occurring at a valley voltage, which is the biasing voltage in the forward direction for this device. Okay, now this particular phenomena, we have to see this particular characteristic phenomena, that is from 2 to 3, the region 2 to 3 operation of the device, which is actually when the voltage is increased, that is the biasing voltage is increased, the current is decreased. So it shows a negative differential region of operation, negative differential resistance region of operation. So here this particular region 2 to 3, the IV characteristic is called the negative differential resistance region of operation of the resonant tunneling diode. As the applied voltage is further increased, the current again rises due to the thermo-ionic emission of electrons over the barrier 3 to 4. The IV characteristic we have seen here, again the voltage after this valley voltage, again if the voltage is further increased, after this valley current again the applied voltage is further increased, it can be seen that the current gradually increases again, that is due to the ionic emission, thermo-ionic emission of the electrons. So that is why this current is increased like this. And the quantum well, IV characteristic and energy band diagram we have seen here, that is shown, this is the condition at which the current which increases after the valley current, which is shown here. This is the energy band diagram for this one, 1, 2, 3, 4, 5, which is marked, 1, 3, 4, which is marked here. So 3 to 4 region is actually governed by the forward voltage applied beyond the valley voltage. So here the current gradually increases, and this current increase is mainly due to the thermo-ionic emission of electrons, and that actually causes the increase of current here. So this is the IV characteristic of the resonant tunneling diode, and this is the energy band diagram for different cases shown here. Now the same thing we have seen here, the same conditions have been shown here more clearly. So here this is the initial portion, that is the current gradually increase reaches the peak value, then coming down to the valley current value at a voltage VV. Here this is Vp and this is VV. Then after this one, the thermo-ionic emission takes place, so the current again increases. So it is shown here again. Then the figure of merit of the resonant tunneling diode is a parameter for the diode, and that is given by the ratio of the peak to valley current ratio. It is the ratio of the peak to valley current ratio, PVCR, of the IV characteristic of the RTD. The normal value of the figure of merit is for the aluminum gallium arsenide device at room temperature is 5. So figure of merit is actually an operational parameter for the resonant tunneling diode, and that is the ratio of the peak valley current ratio, peak to the valley current ratio, that is the peak to valley current, that is peak current to valley, that is if IP is the peak current and IV is the valley current, then the ratio of IP to IV, IP divided by IV is the figure of merit, and that figure of merit for aluminum gallium arsenide device will be almost equal to 5, and this value can be up to 10 for devices fabricated in Indian indium arsenide strained layers surrounded by aluminum arsenide barriers and operated under liquid nitrogen temperature. So the figure of merit can be increased further, that is more than 5, and it may come up to 10 for structures, heterostructures fabricated with indium arsenide surrounded by aluminum arsenide barrier, and that is operated under liquid nitrogen temperature. So the main peculiarity and feature of the RTD is that the RTD can operate at a very high frequencies of the order of several terahertz. You know what is a terahertz? So such a very high frequency this device can be operated. The power delivered from the RTD to an external load is small, and the output impedance is also relatively small. The power delivered from resonant tunneling diode to an external load is very small, and the output impedance is also very small. So this device is sometimes hard to adapt for output waveguides for antennas. So antenna and waveguides, once output said, this device cannot be used or cannot be adapted for some kind of operations, even if it has a very high speed of operation. The output signal is usually of low power. The output signal given by the resonant tunneling diode will be usually of the order of some milliwatts. Since the output voltage is usually lower than 0.3 volts due to the values of the barrier heights and energy levels in quantum levels. And what are the applications of resonant tunneling diode? RTDs are used in static random access memories, pulse generators, multi-valued memory, multi-valued and self-latching logic, analog to digital converters, oscillators and oscillator elements, shift registers, low noise amplification devices, mobile logic, frequency multiplication, neural networks, and fuzzy logic. So with this small description, I conclude the session on resonant tunneling diode. Thank you.